Assalamu alaikum wa rahmatullahi wa barakatuh, and good morning, good afternoon, or good evening to Dr. Rahisham and Dr. Khairul Anwar. So, my name is Ismail Ahmad Mahdi, and today I'm going to present my final year project 2 under the title of Development of Optical Temperature Sensor for Transformer Oil Monitoring System. My supervisor is Dr. Nur Hafiza Ngaji Ken. So, as you can see here, this is our content: introduction, problem statement, objective, literature review, methodology, result and discussion, conclusion, and finally, recommendation. So let's go through the introduction. As we know that electrical transformer is one of the most important things in the distribution system. The process of delivering electrical power from the generation plant to the consumer goes through generation, transmission, and distribution. So in this process, electrical transformer are used either for stepping up or stepping down current or voltage from the primary to secondary. So during this process, there are many kind of energy losses happen while transferring the power from the primary to the secondary coil, either stepping up or stepping down current or voltage. So from this kind of loads, from the kind of energy losses that happen during this process is load losses and no load losses. So the load losses is due to the copper loss, and the no load loss is due to core or iron losses. So all these energy losses are dissipated as heat, which create a thermal stress inside the transformer, which will lead to the rise of the temperature inside the transformer. So temperature is one of the prime factor that affect the transformer's life. Means when we cannot control the temperature inside the transformer, it may reduce its life, or it may cause even serious damages to the transformer. So in order to do so, fiber optic temperature sensor are ideal for oil field transformer temperature monitoring system due to their many advantages, which is immune to radio frequency interference and electromagnetic interference, and high voltage environmental, making them ideal for transformer winding, oil and winding temperature monitoring system. Okay, this is the transformer, oil field transformer, and the sensor will be inserted at the top of the tank. Okay, now we move to the problem statement. So power transformer, is built normally as a compact in design. Means it's compact, means there is less space available for the insulation, and the over voltage and over current would cause a serious problem inside the transformer, and it may cause a failure of the insulation itself and damage the winding. So the over voltage may cause a higher output at the secondary winding and possibly damaging the equipment inside of the transformer. As for the overcurrent, it will heat up the oil, hence it will reduce the efficiency of the oil and the transformer itself, and possibly causing fire or explosion. So in order to there are actually previous methods that are used to detect the temperature. One of them, two actually methods that are used to detect the temperature. The first one is the oil temperature indicator, which is a gauge that is used to detect the temperature. This is actually an old-fashioned method that's still used nowadays, and it requires the person to come to the transformer and then check the temperature, as well as they require current source in order to work, and then also they might heat up, and if they heat up, if the temperature exceeds its normal, they may even damage that the oil temperature indicator itself might heat up and may cause may doesn't give us an accurate reading. As for the second one is the optical temperature sensor. Inserting the optical temperature sensor inside the transformer. Actually, this is also use optical temperature sensor, but the method here is they have to insert, they have to put the temperature sensor inside the winding transformer. Means it's very complex method, and then it requires to be like they need to design it. They need to put the sensor inside the winding when the sensor is being designed. Means you cannot put the sensor after the transformer is complete and everything. So in this project, we are going to develop optical temperature sensor for oil monitoring application. So you may ask, why optical fiber? That's because of they are completely non-conductive, and then they offer high immune. They are immune to electromagnetic interference and radio frequency interference, as I mentioned earlier. And then they are very safe and non-invasive use, which make them ideal for the transformer oil temperature monitoring. So what are the objectives of this project? There are two objectives actually in this project. The first one is to develop an optical temperature sensor for power transformer application, and then the second one is to characterize optical sensor in terms of the accuracy performance. So what are our scopes? So in this project we have a few scopes. We have like 5 scopes. The first one is the temperature detection. It's for fiber-based optical temperature sensor method. The range of the temperature is from 30 to 80 degrees Celsius, or from ambient temperature to 80 degrees Celsius. And then the third one is development of sensor and test it using the Ocean Optic software, which is the software used to get the reading. And then they characterize the sensor by measuring its intensity for different temperature interval. And then the last one is to detect the temperature based on optical optical fiber bend shape type. So now we move to literature review. So first of all, what's optical temperature sensor, and then what's in to be more accurate, we use plastic optical fiber. So what are the plastic optical fiber? The fiber in which both core and cladding region are made by plastic or polymeric material, also known as plastic fiber, and short-term POF. And then, as we can see here in the figure, this is the fiber, this is the the top view, and then this is the core, and then this is the cladding. And then here is the side view. We can say this is when the light transfer through the cladding, through the core of the sensor. It goes like this, and then it hits like this until it reaches its final destination. So the advantage of the POF, or plastic optical fiber, it has low production and packaging cost. It's cheaper. It is soft and non-brittle, hence it offers a great bending without much crack. Means compared to the glass fiber, they can't bend, but this one it can bend easily. Does not have any emission, and it's immune also to noise, and then it can be run alongside by power cable. Means they do not affect at all if they goes through the power next to the power cables. It's more rigid and more flexible, and hence it's easier to install. And then it's light in weight, and it can withstand stress. Okay, so this is the summary of the previous papers regarding regarding sensors. This one is capacitive sensors. Capacitive sensor is actually use temperature between 4.2 and 100 Kelvin. Means this one can use only low temperature range. The capacitive sensor are used for measurement of temperature and humidity in the application. Fiber optic temperature sensor by using interference of selective high mode order. This one is also a glass type fiber. The temperature range is between 100 to 750, which is very high. And the fiber used in interference of selective high mode borders. And then this one is plastic fiber macro band temperature sensor. This is actually close to the one that we are using in this project. Then the temperature range is from negative 55 to 70 degrees Celsius. It used application in temperature sensor with door wavelengths comparison of power fluctuation. And then this one is the FPG, which is one of the most type of sensor. The temperature range is from 30 to 60 degrees Celsius. Actually, this one goes more than this temperature, but in this paper they use it until 60 degrees Celsius also. And then temperature sensor used for medical application. And for our project, last but not least, we use a plastic optical fiber, which is POF, and then the temperature range is from 30 to 80 degrees Celsius. That's the maximum it can go, and used for transformer oil application. So this is our methodology. We can see first we start, and then literature review and theoretical study about the optical temperature sensor and its application, as we mentioned earlier. Characterize the component, and then choose a suitable length of the fiber. This one has been done in the FYP one, which we use we characterize the component, and then we test a different lengths of the optical fiber, and then we choose. And then after that, we fabricate the sensor head. We fabricate the sensor head and remove the cladding, and then we we fabricate the sensor head, and then we remove the cladding, that's the suitable length of the cladding also, and then we characterize the temperature sensor. So here, if the sensor vary with the temperature changes, then we goes to result analysis. If not, we need to refabricate it again, and then goes through the same process, and then result, discussion, and the end. So this is the experiment setup. This is the light source, the optical fiber, sensor head, and then the sensor head will go through the hot plate, and then this is the spectrometer, and then we use ocean view reading in the laptop. So in here, the hot plate, we use the type of like a small container glassware. We fill it with oil, and then we put the sensor inside we put the sensor head inside the glassware with oil, and then we change the temperature in the hot plate. Okay, so now we start the result and discussion. This is the first graph, which is time taken for the oil to heat up. This is just to test the oil. Does it heat up for the hot means? Actually, we test the hot plate, not the oil. We see does the hot plate works or not, and then we use thermometer to see the temperature in from different times. Yeah, and then we can see from 30 degrees, from almost 25, which is room temperature, and then it reach at 80 degrees Celsius, and then it takes how many minutes? It takes around 90 minutes, almost 90 minutes, almost 1 hour and 1 hour and a half. Yeah, and then this is, and then also we wait for the oil, and then we test the oil for it to heat, to cool down from 80 degrees Celsius, from 80 degrees Celsius, yeah, until it reaches 25 degrees Celsius. You can see it takes around also around 85 to 90 minutes. So this one is the sensor head 1.5. This one is no cladding sensor. We use for 30, 40, 50, 60, 70, 80, and then we see how much the temperature range. This graph is not really clear, but yeah, we can see here at 550. At 550, we can see the different length, the intensity from 30 at 30, which is the highest, around 140 intensity, and then we can see it goes down until 40, 50, 60, 70, 80. Means at 80 means the lowest intensity is at 80 degrees Celsius. So from here, this is the graph. We use 550 nanometer and 620 for the intensity, for the wavelength, which is here 550 and the 620, which is the wavelength, and then the intensity we check Yeah, we can see this is our graph. This is a 550, then this is a 600, and this is actually the 550, and then this is a 620 nanometer. And then we see uh, means when the temperature increase, the graph uh, when the temperature increase, yeah, the intensity decreases. So in order for us to check whether the temperature of the oil increase or not, we can see the graph. If the graph decreases, that means the temperature increases, and then if it reach at around 120, the intensity, uh, or I mean 110, yeah, around something like that, 115, and then the temperature reach around 80 degrees Celsius. The same goes for the 550. When the temperature decreases, when the temperature increases, the intensity decreases. Then we can see, okay, this is the linearity of the graph. The 550, you can see, is more linear compared to the 620. And yeah, so now this is the sensor performance, the wavelength. We have 550 and 620 nanometer. And then the sensitivity for the 550 negative 0.42 degrees Celsius, and then the 620 is negative 0.6. As for the linear range, this one is 30 to 80 degrees Celsius. Both of them are 30 to 80 degrees Celsius. For the accuracy, we can see that this one has 97% accuracy, the 550, and then the 620 is 91% accuracy. So we can say this one is more accurate compared to this one. Even the sensitivity, this one is more sensitive than this one. So for the conclusion, we can say that development of optical temperature sensor has been done successfully. And then the environmental was created for the sensor using different medium, which is dry heat oven and hot plate. The dry heat oven we used to define to identify the temperature range from uh, we define to identify the length of the fiber, and then the result obtained that the sensor wavelengths change, and the intensity reduction for the temperature in a different interval means the wavelengths change when the temperature decreases or increases, depends on either the interval of 10 or 5. So the sensor, at the end, we consider the sensor exhibit a high accuracy of about 97% at 550 nanometer wavelengths compared to 91% at 620 nanometer wavelengths. As a result, we can say that the 550 wavelengths is more accurate compared to the 620 nanometer wavelengths. So now there are few recommendations that would like to suggest for future studies. So one of them is, first, maybe you can be used the type of sensor. Maybe because the POF, as I mentioned earlier, it can withstand only limit temperature range, but this one, the fiber Bragg grade temperature sensor, can withstand until 300 degrees Celsius, which will give us more accurate reading. But the disadvantage of this one cannot be bent. Means when it's bent, because it's a glass fiber, so it may break. And the second one is where we use a real transformer to test it, which we get more efficient data. In our case, we couldn't test in a real transformer because we didn't have the resources nor the time to do it. So we suggest that the future result may test it in a real transformer. So that's all for the presentation, and thank you very much. And I hope to see you in the Q&A. Thank you, Doctor.